something impossible showed up in the mail. Not real mail, of course. This was digital mail. Data. Packets of light sent across the void and captured by a giant golden eye in space. When astronomers processed the image, they saw something that shouldn't be there. It was a photograph from the past, the very distant past. It showed a galaxy, but not just any galaxy. This one was a spiral. It looked familiar. It looked, in a way, like home. It looked like our own Milky Way galaxy, but it was in the wrong place. And more importantly, it was from the wrong time. The light from this galaxy traveled for over 11 billion years to reach us. It was a message in a bottle from a time when the universe was a toddler, just 1.5 billion years old. The astronomers who found it gave it a beautiful name, Alaknanda. The name comes from a river in the Himalayas, one of the two headstreams that join to form the sacred Ganga. The other headstream, the Mandakini. The name is poetry. It suggests a shared origin, a sibling relationship. Alaknanda is our galaxy's twin, born in the same cosmic river of time, seen in its infancy. And this twin is precocious. It's a child prodigy. When we look closer at Alaknanda, the resemblance to our modern Milky Way is uncanny. It has two distinct symmetric spiral arms. These are not faint, wispy tendrils. They are well-defined structures wrapping around a dense, bright central bulge of stars. This is the hallmark of a grand design spiral, the most majestic and orderly type of galaxy. Furthermore, Alaknanda is a hive of activity. It's churning out new stars at a furious pace, about 20 times faster than the Milky Way does today. This discovery was made by two astronomers in India. Imagine their work. The story of the universe, as we've written it so far, is one of gradual construction. It's a bottom-up process. After the Big Bang, the universe was a nearly uniform fog of hydrogen and helium gas, threaded with invisible webs of dark matter. Gravity began its slow, patient work. It pulled matter into the densest parts of the web. Small clumps formed first. These clumps became the first stars. These clumps became the first dwarf galaxies. Over billions of years, these small galaxies collided and merged, like streams flowing into rivers, and rivers into seas. A grand spiral like the Milky Way was the end product. This model is known as the Lambda Cold Dark Matter Model, or LCDM. It has been incredibly successful. It predicts the large-scale structure we see and explains the cosmic microwave background radiation, the afterglow of the Big Bang. According to this model, the early universe was too hot and too chaotic for large, stable disks to form. Any nascent disk would be quickly disrupted by mergers. The universe needed time to cool. This process was thought to take at least 5 or 6 billion years. Alaknanda throws a wrench into that tidy timeline. It exists just 1.5 billion years after the Big Bang. It's a calm, ordered disk in a sea of chaos. It's not that the theory is wrong, necessarily, but it's definitely incomplete. This discovery would not have been possible without our new eye in the sky, the James Webb Space Telescope, or JWST. It is an engineering marvel. Launched on Christmas Day in 2021, it traveled 1 million miles from Earth to a stable, cold orbit. Its primary mirror spans over 21 feet. It's designed to see the universe in infrared light. This is crucial. Because the universe is expanding, light from the most distant objects gets stretched, shifting from visible into infrared. JWST was built to capture this ancient stretched light. Think of it this way. Looking deep into space is like looking back in time. The speed of light is finite. The sun is 8 minutes ago. Andromeda is 2.5 million years ago. JWST is a time machine capable of looking back over 13.5 billion years to see the first stars and galaxies switching on in the cosmic dawn. The team that found Alaknanda used JWST to do more than take a picture. They performed spectroscopy. A spectrum is like a chemical fingerprint. By analyzing its light, astronomers could tell what it's made of, how fast its stars are moving, and how quickly it's forming new ones. It was a rotating disk. Not a chance alignment. The data was unequivocal. The arms were spinning. The center was bulging. The galaxy was real, and it was ancient. Each new instrument reveals a universe more complex than we imagined. Alaknanda is one of those mysteries, delivered by a golden eye in the dark. So, what does this mean for our understanding of everything? Discoveries like this are where science gets exciting. It's where we have to go back to the drawing board. Did the first seeds of galaxies grow faster than we thought? Was the gas in the early cosmos colder, settling into stable disks more easily? Or could there be something about dark matter we don't yet understand? Something that encourages rapid structural formation? This isn't the first time JWST has sent puzzling postcards. It has found galaxies that are too massive, too bright, too mature for their age. It's a recurring theme. Alaknanda is not just an outlier. It's compelling evidence that our cosmic storybook needs a new chapter, or at least a major revision of the first few pages. Our Milky Way was not born in its current spiral form. We know it grew by swallowing smaller galaxies. Astronomers have identified fossil remnants of two of its earliest building blocks, ancient streams now named Shakti and Shiva. They collided with a proto-Milky Way over 12 billion years ago. This fits the old story of chaotic mergers. But Alaknanda suggests another path was possible. The work now falls to the theorists. They will tweak star formation, gas dynamics, dark matter properties, trying to grow an Alaknanda in their digital universes. If they succeed, we find a new mechanism. If they fail, the mystery deepens. Either way, our origin story becomes richer. In the end, Alaknanda leaves us with a sense of wonder, but also a slight unease. The universe feels a little stranger, a little more mysterious. The calm, orderly march of cosmic evolution has been disrupted by a beautiful anomaly. We look at this distant twin of our own galaxy, a serene pinwheel spinning in the dawn of time, and we see a reflection of ourselves. It's a reminder that our origin story is still being written, and the universe is a far more creative author than we give it credit for. This discovery is a profoundly human story. It's a story of curiosity, of persistence. It's about building a magnificent machine, sending it 1 million miles away, and using it to catch faint, ancient photons of light. It's about a team carefully analyzing that light and finding something that challenges the consensus of generations. Science is not a collection of unchanging facts. It is a process. It's a conversation with the universe. And sometimes the universe talks back and says, "You're on the right track, but you've missed a crucial detail." Alaknanda is one of those crucial details. The early universe was not just a chaotic mess. It was also a place of surprising and rapid creation. Order could arise from chaos much faster than we thought. And so we are left staring at this impossible photograph, this ghost from the cosmic dawn. If the universe could build a galaxy like our own so quickly, so long ago, what else did it build in that ancient dawn?